sorry, so we only have 3 more methods to write. 4 if we include the, sorry. 4 if we include the toString method, which all I'm going to do is actually I'm going to just skip ahead and I'm going to steal that from yesterday, from what I did yesterday. So we're going to do public toString. We're going to steal it over here and let's put it in there, right? And all this will do is now when I run our code, it will actually only print out, it's not going to print out the nulls anymore, right? That's all it's going to do, right? And what I did is that it had, you know, my output is now a, you know, open bracket, take every item in there except for the last item, and then take every item except for the last one, glue it to the output that already exists, and add a comma and a space after that. And then the last item, it doesn't need a comma or a space after that, so instead just slap a bracket on the end of that. And the reason I couldn't do everything in this was because it was a sentence posting problem. Then I'd have a comma and a space after the last one, which would look incorrect. All right, so let's go ahead and write GetInSet. Now those methods are pretty easy too. So public get, right? So we're going to get something at index at some index, and we're going to return it. And it's of type E because, you know, that's what's stored in the array. For right now, I'm going to squash this error by saying return null. Okay. All right. So the first thing we want to do is just like with the add method. What if it's out of bounds, right? So the out of bounds is slightly different this time. So first, obviously, if index is less than 0, that's still a thing we don't want, right? Or, now last time we had this, greater than or equal to size, right? Because we could add to index size, right? But because we're getting something, there's nothing at index size currently, right? So instead of just doing that, we just do if it's greater than or equal to, we had this last time, right? Which would be basically we could add to index size. So now we can put greater than equal to size. And that means basically if we try to get something at index size or higher, right? We had up here, if we try to get index 5 in this example on the board, then basically we give them an error. So this basically prevents us from accessing those nulls that don't exist. And of course what we're going to do here is throw new, you know, array index out of bounds exception. Okay? Okay, and all we have to do at this point is actually fairly straightforward, as you can imagine. Instead of returning null, we're just going to return, well, if it's not out of bounds, I can go ahead and just straight up return it to the user. Return data index, right? Just return it, right? Okay, set's pretty similar. In fact, I can just copy paste this for the most part. Public E set, we're going to take index and we're going to replace it with E new item, right? We're going to take the old item and replace it with a new item. And here what we're going to do is that, again, same thing. We can't, if it's a bad index, same bad index, right? Then we can't change it out. So we give the user a bad exception. Otherwise, we're going to keep track of the old item for them. Old item is equal to what's currently there. So data item. So old item is equal to data, what's in the current index. Then we're going to go ahead and replace it with the new item. And then we give the option to the user or to the programmer that, hey, would you like that old item that we just removed? If you do, here it is. Otherwise, you can just throw it away, right? Nothing too scary about that, right? All right, continuing on, that leaves only remove. So I'm going to go ahead and copy. Actually, I'll just go ahead and write it. So remove. So the first thing we need to do is do public remove, and let's figure out what it needs. The return type should be E, and we're removing something from int, you know, from a certain index. Int index, right? And we are going to return that item. So right now we'll say return null. And again, with all these methods that we're doing that we're just grabbing stuff at random locations, if index is less than 0, or if we're trying to remove something at an index that doesn't exist, greater or equal to size, throw a new array index out of bounds exception, right? So we throw a new exception. Okay. So, however, getting into if we're removing an item right from this, we can't just do this as much as we would like to, which is that E removed is equal to data at the index, and then just return the removed item. As much as we'd like this to be the end of things, it's not, because we have to overwrite everything. So going back to the example up on the board, right? The idea here is if I've got this, if I want to remove what's at index 2, right? The end result is that if I'm removing C, then Q and Z have to snap back into place so that there's no gaps, right? Okay. All right. So the size of this thing is current. So C, Q, Z. So let's go through this. Okay. So I want to remove what's at index 2. So what I can do is actually, so everything has to shift to the left as opposed to the right this time. So what I'm going to do is I'm going to start at this index. And I'm going to say, okay, whatever to the right of me, store it in here. Okay? Or, yeah, whatever's to the right of me, store it in here. So I'm going to take this guy, and so C is going to say, whatever's to the right of me, take this and copy it over. So C will be replaced by Q. Then we go over to index 3 and say, whatever's to the right of me should be stored here. Z. We've successfully, so first off, we don't have to go over here and say, okay, 4 should copy null over, actually, because we can just stop right here now, because A, B, Q, Z, right, we removed one item, we removed the C from this list. This list is now 4 long, right, from the user's perspective, right, because, it only has 4 items to it. The size prevents me from seeing that leftover Z over there. So we're just going to leave that C lazily there, even though because once we add something, it's going to get erased, right? It's going to get copied over. Okay. Which reminds me, we should probably if we're removing an item, we should totally remember to reduce the size by 1. So what we got to do is that we're going to start at the index that we're removing an item from. So int I is equal to index. I is less than, so while it's less than size minus 1. So while we're less than the item, right, because we want to start here and copy from the left, copy from our right, and then go here and copy from our right, but we don't want the last item. So we go size minus 1. As opposed to size. And then we do I++. Okay? And then what we do, we say data index. So we say the thing at, it's data I, the thing at my current location, I'd really like to store inside of it. I'd like to store inside of it what's to my right, which is at I+1. So I'd like to take the thing to my right, and store it at myself. All right, so of course, and then size minus. Now you'll notice that, and that's it. Notice that there's no like reallocate method. Like if we have too many open slots, we shrink it. We could do that, but we don't. But one thing I don't want to really get into that. We could totally do that. Like where basically if it's shrunk to a quarter of the original size, like 3/4 of the array is filled with nulls, we shrink it. But honestly, that's unnecessary. And I mean, that's that's something I could easily say that's left as an exercise to the users, because all you have to do is just divide the capacity by 4 and then, create a new array and copy everything over. It's not too hard. So we only double when we're adding something. So remember, from your quiz, the capacity it starts out at 10, and it only increases when we actually have to create a new array, right? So that's why the answer was 10 in our quiz, and for the capacity, and the size was 3 because we added 3 items to it. Okay, I was making sure it was an emergency but nope, it's just my wife and mother-in-law talking with me in a group combo. So all right. All right. So so that's it for remove, and that's pretty much it for ArrayList. The only other thing I can think of that we wanted to go over was public int index of, right? Right? So we wanted to go through and say, hey, do you have this, item in here? Right? What's the index of this item? Right? So in the way, remember, this works is that we're going to ask for this item. And so let's go ahead and go through the loop. For int I is equal to 0, I is less than... Oh, and I also should probably test it, but we'll do that in a bit. Okay, so for I is less than size, I plus plus, if, and this one's fairly straightforward, if data item, so if the item, if the data at I is equal to our item, assuming I can remember how, again, this keyboard is just slightly smaller than my old one. So equals the item we're looking for. So if this is holding the item we're looking for, we're going to just return the current index we're at, right? We find the first item, we find the first index that holds the item we're looking for, okay? But if we go through the entire thing and we can't find it, return -1 to tell the user, hey, that doesn't exist, because -1 is an index that doesn't exist. So you should be able to figure out that you can't use that. All right, so let's go ahead and test this. For int I is equal to 0, I is less than 100, I'm plus plus. And what we're going to do is that we are going to list dot remove the item at index I. So this will kind of create a weird interweaved thing. Of course, it's not going to do anything unless I actually, print it. Let's actually print it before we do the operation and then after we do the operation. So there we removed. It's not actually that weird. So we remove 999, and then we go over and say remove the thing at index 1. Well, index 1 is now 997, so we remove that. Remove the thing at index 2. Well, now that thing is, 995, so we remove that, and so on and so forth. So we remove the first 100 odd numbers from that. So that works. I'd say it works because, copies things over. It's my kind of the expected result. We want to make sure that's the expected result, though. We can just remove 0. Add all the items in order, and then remove the first 100 items. So that seems to work just fine, right? Okay, so, and then system.out.println index of, let's go ahead and see where's the index of the number 0 in this list. It's nowhere. And where is the index of 100 in this list? Well, it should be, I think, index 0? Yeah, it's an index 0 now, because we removed the first 100 items in there, 0 through 99. Okay, so that works. Fantastic. Okay, so this is how ArrayList pretty much works underneath. So let's go ahead and see what kind of method you'll need to write. Yes?
Are lists different from ArrayList?
ArrayList is a type of list, remember? Okay. So right, if I go over here into, so now let's go ahead and say list examples, because I'm about to do this. List method examples. And this part is going to be a bit relevant for your homework here. So, right, if I'm going to create a list, right, so a list is a type of list, right, because an array list in Java implements list, right, so it's a type of list. So what I can do is say list of integers is equal to array list, okay? And of course, it's giving me a bunch of errors because I have to import these things, but, you know.
So when you create a new list, you always have to specify what kind of...
Yeah, what kind of list it is. I can't just say list over here because list is an interface, if you remember, right? It's just a bunch of method stubs that haven't been implemented. And then what we're saying is here is that an array list, right, is an implementation of it. It's got all the stuff that a list needs to survive, essentially. So we're saying a list, you know, it's saying what kind of list do you want? An array list. And this is as opposed to the other type of list we're going to learn about, linked list, which is only giving me an error because, again, I haven't imported it, right? So there's two types of lists. So in Java, so in programming, though, if we have two types of a thing, right, what does that mean? You know, when it seems like only one would do, right? It means that one is better than the other at something, right? It means there's advantages and disadvantages. And we'll go into that once I go over, like, this little part, because I want to make sure we get this. So let's write a very basic method called public static void, you know, let's say toString, okay? Sorry, public static string toString. So this is a static method. And what it's going to do is that it's going to take in a list, okay, of items, and it's going to turn it into a string, right? It's going to return a string representation of the list, okay? Make sense? Nothing too exciting here. It says that, all right, I should turn it into a bunch of, I should add arguments to this. All right, so the first thing is that basically, that was weird. There's a question mark in there. What the heck is this? It's madness. This is what this is. Essentially what it is saying over here is that this is a list of, right? So when we're dealing with, so there's essentially two different ways we're going to have to deal with generics. The first way is dealing with them in this context, where we've got them basically where we're creating an object, right? So we're creating a class, and we're saying that basically we need to, we basically want to put something of some type, and the class is going to hold all the same type in it. So this is typically used with collections of things, like a collection of integers, which is just a list, you know, so a list is a collection of strings, all the same type, and basically replace all the E's with something. We can also do that with methods. I think this might be the wrong method to use to start with, though. I think I'm going to start with a different example, which is going to look harder, but is actually easier to explain. Okay, so let's go ahead and actually do something that's different. Sorry. I'll go back to this one. Public static int sum. Okay, so this one was from the homework last year, and I'm going to take this out and replace it with a new problem. But this was like from the homework last year that you got, which is simply said, given an array list of integers, right? Given an array list of integers, I'd like to sum it all up. Okay? You know, just give me the sum of all the numbers in this array list. Okay? So, okay, need a return statement. So let's go ahead and, you know, return, let's see, return sum. And all we have to do there is like say, so we're going to start out with an int sum is equal to 0, and then we're going to add all the items to it, and then return the sum. Okay? So the way we can work with that is like for int I is equal to 0, right? We can just iterate through this like we would at any array, right? Except instead of saying, you know, except a couple differences. First is list.size instead of array.length, right? So I is less than list.size instead of array.length, and then I++. Okay, notice I didn't put any generics here yet. Again, this is to remind you that generics are kind of pretty useful, right? Sums and array list of ints. Okay. So we're just going to, and you can imagine how this goes. All we're going to do is say int num is equal to list.get. So instead of saying list I, right, as we would with an array, right, with an array it would be this, right, the subscript notation. Instead, we're going to do list.get. What's that index, right? Of course, we can't because it's an array list and it holds objects, right? So I'd either have to cast it like this, right? Okay. Except that, you know, I can totally use generics here, actually. And I can just say, actually, this takes in an array list of integers. And now that will work, right? I can specify that this method only works on array lists of integers. That's pretty nice, right? I can specify that this method only works on array lists of integers. And this is useful because can you imagine the nightmare I would have if I implemented it like this, right? Plus, you know, and this is all I would need to do to calculate the sum. Convert it, you know, cast this into an integer, and then set equal to num, and then sum is plus equals num. Actually, we can just condense that to one line, of course, and just say sum plus equals the number we got from the list, right? But can you imagine that this is a bit of a nightmare because I can right, without generics, I could totally pass an array of list of strings into this, and it wouldn't give me an error until I actually ran it, right? Until I actually tried to cast something. So again, generics prevent me from shooting myself in the foot here, saying this is an array list of generics. So I don't need array list of integers. So I don't need to cast anything over here. Okay, so that's great. Okay, what about like a, you know, more, you know, kind of method where it's not, where it might be something else. Okay, and that brings us back to here. What if we've got like something like this? It's an array list of anything, right? So what I'm going to do here is that this method over here, I didn't explain what it's going to do, but figure you probably have a good guess from the method, that this just simply takes in an array list and turns it into a string, right? Creates a string for the array list, okay? And again, I've got this warning over here, and I really don't need it, right? Because every object has a toString method, but I really don't like that warning because it's just, you know, an eyesore. One thing I can do with this kind of method is that I can kind of just say this is a generic. This takes in a list of all the same types over here, and I'm going to use T because I'm not inside of a class. I'm going to use T because I'm not doing this for an instance method. I'm going to use T here just to specify this. And what you can do is that in a method in here, you can say that basically this is a list of all the exact same stuff by just doing this notation over here. And that looks a bit weird. I go into a pretty good write-up about this on the homework, which I'm busy slightly rewriting just to give you guys different problems from last semester. But I'll go ahead and pull it up just for you right now. So I think that's list functions PDF. Right. So I'm going ahead and So here we go. And I go into like static generic methods, right? So basically, here's a method that we might want to write. Where this is something. Suppose we want to write a method in, which given a list, checks to see if a list contains that item. Footnote, I said. This exists as an instant method under a different name, and yeah, the contain method. So let's just pretend that the contain methods doesn't exist. We don't know what type this item is. We don't know what kind of stuff the list is holding, and that's going to change from one program to another, but we know that this item should be the same type that's in the list, right? Right? This is going to be the same as this one. However, if we write it like this, it gives us an error, and it tells us that E cannot be resolved into a type. I put T there. It doesn't matter on my side. It happens because Java doesn't know you want to use E as a symbol for a generic. So you just tell it, I'd like to use this symbol as a generic only for this method, right? Once this method is done, you can pretend that there's no such thing as generics. Does that make sense? This is just simply saying that it's a generic. Now, you don't have to use this when basically that we know what type is going into the method, right? When we don't know what type is going into the method, we want to use this. When we do know what type is going into the method, we want to use, we can just tell it. Like, going back to our previous example, ArrayList, we knew what type ArrayList had, right? So we could just simply say it's an array list of integers, right? And just pass it in there. We didn't have to put anything funky over here. We knew what type it was. It's an array list of integers. It only works on integers, so pass that in. Here, we don't know what type it's going to be, but we know everything's of the same type. So we can just say this. There's one alternative over here that that Eclipse suggested to us, and that is that we can use the wildcard over here, which just simply says, yeah, anything can be put in here, but I guarantee you it's all the same type. Okay? That's the other option, which I didn't write down there. But we'll go with this because that's what I wrote down on your homework. And all we have to do here is just simply say for. Now, what's cool over here is I can use the for each loop again. So for t item in the list. So for every item of type t in the list, right? I can, let's go with string output is equal to that, and then for every item in the list, output just simply gets concatenated with getItem and a space. Oh, and yeah, I need to end it with a semicolon, and then return the output plus a bracket at the end. Okay, and we'll see that basically if I create a list of stuff and do list.add, so let's go ahead and see this. So let's go ahead and add for int I is equal to 0, I is less than 10,000, I plus equals 5. So we're going to just start adding numbers to this list. So list.add I here, and then what we can do is that we can print out the sum, right? System.out.println sum of the list, right? Give me the sum of all the numbers in the list. And what is it saying? It's expecting an array list, and I'm passing in a list. Okay, well that's simple. I can just simply say that this is a list instead too, right? No problem. So it takes in a list there. And so it takes in a list as an argument, which means I can pass in a list of any type into that, right? But if I said array list, I could only pass array lists in there. So if I switch this back to array list, let's just keep it as list because the other one's a list too. Okay. So now I can do that and run it, and error exists. What error? What error? Oh. For every item in, I called it L here. And that's the sum of all the numbers that were added to that list. What about, and I can also do system.out.println. Okay. List.add, not list.add, but toString. List. So, well, that didn't work. For item in the list, why didn't it print out? So it printed out a bunch of spaces, but item.toString, why didn't it work? Well, it printed out a bunch of spaces, so that's very interesting. Why don't we go ahead and separate everything by new lines and see what happens then? Okay, I have no idea why it wasn't printing, but every item was in there and was getting added. I have no idea why it wasn't printing the string though. Maybe because it was just so bloody long. Okay, but okay, these methods work. So Okay, but getting back to my original question of like, so why are we learning? So there's linked lists and then there's array lists, and we're done with the array lists. But we really need to get at the point of like, why are we learning two different types of lists? Why are we learning them? And the reason is because basically lists have one advantage. You know, some lists are good at one things and others are not good at things. And to understand that, we need to start talking about big O notation, okay, and algorithmic efficiency, and basically costs. All right, so running software does have a cost associated with it, right? Like programs, they have costs. You need to use something. You have to use some kind of resource to run your programs, right? So let's start with the most valuable resource in the world. Nothing is more precious than this resource that you use every single time you run a program. What is this resource we use?
Memory.
Memory you can buy. It's not that it's not valuable.
Processing power.
Not valuable. You can buy it.
Time.
Time. You cannot buy time. You cannot buy time. Therefore, it is the most valuable thing in the universe. So that is something that is used. That is the most valuable resource we have, and it is basically everything that is predicated on, for the cost. That is all that us as computer scientists really care about, and as programmers we care about. The cost of time. Okay, not true. We do care actually about memory. We do care about memory. Memory comes in second because that your programs do take up memory. Time and memory are the two most important things. Time the most important of all, but time is the most important because again, time is money, and because you can't buy more time. So it's basically reducing the time that things take is very valuable. So as a result, some data structures are really good at taking up less time for some functions than other data structures are. Okay? Memory, a lot of them are going to use basically close to the same amount of memory. Okay? But there's also other costs that are valuable depending on the context. Like memory, right? You can imagine that basically if you for some reason didn't care about time, right? But you were working on like a small embedded device, right? It doesn't have much RAM on it, then that suddenly is a constraint, right? If you care about the battery life of your phone more than like how long the process will take, then energy is certainly a cost. That's really popular these days. Energy, the amount of energy that basically, computation does cost energy. You don't care about it for the most part because the computer you're using usually is plugged in somewhere, but if you're using a laptop like so many of you are, I'm pretty sure most of you care about it because, it's slowly chugging away at the battery reserves of your life. So basically, if you can reduce the cost of checking for a Wi-Fi signal every so often, that's great. Reducing the cost of basically, communicating with other devices, reducing the cost. One way to reduce the cost is like, displaying stuff on screen, making it darker. So energy is another valuable cost, especially useful in like if we're like in areas where we can't get more energy, right? So everything is battery powered. It's especially true of like military situations. Like almost every paper I remember, like from the 2000s that I had to read about like energy efficiency, they always like had at least a paragraph mentioning and like it's important for battlefield applications. So please give us funding, DARPA. So but it's you got to justify why the stuff you're doing is valuable, and reducing the cost of energy is always valuable. So time, memory, and energy. But the main thing we're going to focus on is time, because it's also the easiest to see how long it takes to do something. How long does it take to, do certain operations take? And the nice thing about it with ArrayLists is that they're good at, as I mentioned, they're good at some things and they're terrible at others. So I can actually kind of demonstrate very easily what goes on. So let's go ahead and just start by class. So let's go ahead and put in a new class and say it's in big O evening. So let's go with big O example. Okay, so I'll write some methods in a bit, but actually I'll do this by writing a bunch of methods that'll just demonstrate this. So the first is, let's go with public static void. Now, unfortunately, because computers have gotten so much faster, and this guy's actually, I think, incredibly fast, I might actually have to get the numbers really big before we start seeing like kind of a difference going on here. So ArrayList. So this might flop. ArrayList creation. So, all right. So the first thing I need to do is be able to, if I want to figure out how long something is going to take on my computer, I got to have a way of figuring out how to measure time on my computer. That's actually harder than it sounds because we actually have to agree on what time is. So for right now, we're going to agree that time is the number of seconds that have passed since 1970. I am serious. That's how time's calculated on your computer. Because you also, I mean, there's this whole rant that I've seen online that I can send you guys a link to, but it's basically that time is terrible because we've switched calendars multiple times. And by the way, there are different calendars because different countries use different, you know, we're all on the standard Gregorian calendar right now, but, you know, if you're part of a particular religion, like Jewish calendar goes by a lunar calendar, and we have leap months. So, yeah, not leap days, leap months. So, now, and these computers do have to account for leap seconds. So so time is very messy, but we don't have to worry about that because we're just going to let the smart people who programmed it deal with that. So we can use system.nanotime, and that will return the number of, the current time in nanoseconds. Actually, that's probably too small. Let's go with system. I think, current time millis, because milliseconds is actually going to be easier for us to use. So milliseconds, because nanoseconds gets a bit fuzzy. So what we can do is that we can, if we want time, how long something is going to take. This gives us a rough estimate of how long this can take. Create a long that says start, okay? And then a long, that's the time, basically the time in milliseconds when this starts, when I call this. So if I were to just call this, it would be system.out.println start, right? And actually, all I have to do is call this because I got println in there. So ArrayList Creation. Okay. And it's going to print out this is the time and in milliseconds, and you notice that it's going to change, because, basically every millisecond is going to change. And so I can start it then, and then if I want to figure out how long the process takes, I can, do a bunch of code in between these two statements, a start and an end. And then I can say the elapsed time is simply system.out.println, end minus start, because the end is going to be bigger than the start. And this will tell me how many milliseconds have passed, which should be about 1 millisecond has passed. So it goes pretty quickly. That might be, rounding error too. It's rounding error. So sometimes it's 0, sometimes it's 1. So, all right. So with that being said, let's go ahead and see what happens if we just simply create a really big array list. So let's go ahead and say ArrayList test is equal to a new array list. Okay. It's going to be an array list of integers, just like everything else is. And I'm going to add, what's the maximum? So what is the maximum size for for an integer? Approximately. How big can I make an integer approximately? About 2 billion, right? So that's about as many as I can hold in here because the underlying array is going to be about that big. Right? You can only make it to 2 billion. So let's see if that's big enough. So for int I is equal to 0, I is less than let's go with, that's 1 million. So let's go with 100 million. I plus plus, maybe that will be too slow. I don't know. I'm just going to figure out until we get something that is test.add. And this is going to be this isn't going to be a particularly hard add operation. We're just going to add a bunch of zeros to this list, right? Just add I. Why not? Okay. So we run this. Okay. So it is actually going to take a good amount of time. I just want to make sure that basically. So it took 4 seconds to do that. If I take off, if I divide the amount of things I'm adding by 10, as you can see, it takes, this should not be surprising to you that basically if I divide the number of things I'm adding to it by 10, that it takes, a tenth of the time to do, approximately. And yes, there's some variation. Why? Because computers are funky like that, especially on such a small sample like this. Measuring in milliseconds is very small, so dealing with 10 million items now is pretty small. So I'm just adding this onto the back, right, of the array, just simply adding one item on the back of each other. So now I'm going to go ahead and add, so instead what I'm going to do, right, and we were getting 5 seconds about, right? About like 4 milliseconds, right? So instead of adding it to the back of the array, I'm going to add it to the front. And that should make a huge difference here, adding it to the front. And why can anybody guess why? Yes. Because yep, that's exactly right. Because when I'm adding it to the end, I'm just slapping it onto an empty space. But if I'm adding it to the front, then everything needs to shift over to make room for it, right? So that's going to take a bit more work. So let's go ahead and watch what happens now. And I'm like going, please work, please let this example work, because it's still going, by the way. I guarantee you, like, let's pull up the console. It says it is running. It is running. And it's still going. It takes a lot longer to do that, in fact. So we can kind of conclude. So let's go ahead and actually give it a bit of an easier problem, okay? So let's divide by 100 and see if we get anywhere. So now we're only asking it to do 100,000 methods. So 100,000 runs of this, okay? Oh, wow. So it took like 100 times longer to do, right? Because I had to divide by 100 to get the same result there, right? So this tells us something. ArrayLists are great at slapping something onto the end of something, but they're absolutely terrible when it comes to adding to the front. Okay. Now, I can't just simply say like that this takes a certain amount of time on my computer, and that's the amount of time this takes. I can't really use that because this computer is different than this computer, and it's certainly different than the computer that the computers that were around like 20 years ago, and this computer is going to be probably much less powerful than the computers that are going to be around 20 years from now. We're always wondering if we're approaching the end of Moore's law, because we're making our transistors tinier and tinier, and I don't think there's too much room to make them tinier. So we'll see. So I can't just simply say it's fast or slow, right? Because that's also going to depend on context, right? Waiting a couple minutes, 40 minutes, is nothing compared to the length of a year, and certainly nothing compared to the amount of time humanity's had for computing power, and that's nothing compared to the amount of time humanity's been around. So time is very large. On the other hand, so that amount is relative. So what we're going to do is that we're going to come up with we have a mathematical notation to say how quick things work. Now, adding to the end of an array list is a pretty quick operation the vast majority of the time. Okay, the vast majority of the time, adding to the end of an array list, you just simply say, "Let me insert this into the array," and we're done, right? That's what we showed, right? If you remember the code, because I can just pull it up, the vast majority of there's only a couple of operations that go on to that, which is that I check to make sure it's not out of bounds. Okay, that's a single check over there. If the size is equal to capacity, if I'm adding to the end, then basically worst case scenario, I do sometimes have to reallocate and have to double my memory, and that means I do have to do something like a shift operation. But I don't have to do it that often. I only have to do it when I double the size. So from 10 to 20, then 20 to 40, then 40 to 80, and then you can see how it gets, how basically as the array list gets bigger, the doubling happens less and less often, right? So now I don't have to, and then I don't have to do the shift. But if I'm adding it like to the beginning, then not only do I have to do this reallocation operation, I have to do this shifting operation. So this gets us into, but in the grand scheme of things, that's actually not that quick. But we call, sorry, that's slow. But we call this operation a linear time operation, O of n. So I'm going to teach you basically 2 terms today, probably 3 if I can, yeah, probably 3. So I'm going to teach you 3 different types of classifications for the amount of time something takes. So, and I'm going to just throw this out here. I'm not working to give you a working mathematical definition of this. I'm trying to go for like a feeling definition of this, a more working definition of this. So nothing mathematical. We're not going to do any hardcore proofs here because those are boring. And those, to be honest, are covered in other classes. You know, I think in the Math Concepts 2 class, we cover big O notation much better. Like, have you taken Math Concepts 2?
I'm taking it now.
And are they going over big O notation? Yeah, so this is much more of a, what does that feel like to us? Okay, so we're going to learn basically what 3 things feel like. O of 1, oh, let me get it over on the board. O of 1, O of n, and O of n squared. Okay, and these are, so big O is just what mathematicians use, and technically I'm not even using it correctly because technically the mathematicians are all about something called big theta, and computer scientists just use big O because we're terrible mathematicians. But so we use big O, and I'll get into what that means, but O of 1 is short for constant time, linear time, and then is O of n, and then O of n squared, that's a quadratic function, so this is unsurprisingly called a quadratic time. Okay? Now what does this mean? Constant time means no matter what you do with a function, it's always, no matter what your input is, it's always going to take the same amount of time for this to run, no matter what, essentially. Okay? A linear time operation means that the bigger your input is, the more time this is going to take. Okay? And quadratic means that basically if you increase the size by 1, then you increase the overall work by n. Okay? And I'll get into how that works out. But so let's go ahead and look at some just basic functions that are pretty simple for us to tell. So let me go ahead and show you an example of a constant time function that we use, that we've already done. 2 of them, in fact. So we already wrote 2 very easy to see constant time functions. Size and is empty. Okay? These are what we call constant time function. It doesn't matter how big the list is. Okay? These operations are going to take exactly the same amount of time. Right? It doesn't matter how big the list is. Returning the numbers, this may not be obvious, but no matter how big, returning the small numbers takes the same amount of time as returning the big number, right? Right? It's just a bunch of bits, right? It's how big is an int? It's 32 bits. They're all 4, so all integers, no matter how big they are, they all take up 4 bytes. So it takes the same amount of time to return 4 bytes that represent a small value and 4 bytes that represent a big value, right? So no matter how big the list is, doesn't matter if it's size 1, doesn't matter if it's size, it doesn't matter if it's size 1,000,000, right? And I can show you that. Public static void, okay, right? Test constant. So we're going to just show you that this is a constant time operation. So again, we're going to create an array list called test, and we're going to just track the amount of time it takes. Okay. And anything we want to test how long that takes, we're going to put it in here. Now, over here, because I want to test how long the size function takes to run, I'm going to create my array outside of it because I only want to test how long it takes to run the size function, not how long it takes to add things to it. I'm just testing how long that single function runs. So for int I is equal to 0, I is less than, right? So I'm going to start out with a big number first, I plus plus, test.add 0. Just going to add a bunch of zeros here, and then we'll just see how long it takes to call list.size. Oh, sorry, test.size. Right? Mind you, I'm using the ArrayList, the actual Java ArrayList, but it works basically the same way as the one I wrote, so that's fine. So I'm gonna add a million items to it, and then oh right, I have to test the right one, so test constant so run this. 0, it takes no milliseconds whatsoever to run this, right? It takes no time whatsoever. Doesn't matter if it's big, right? There's a lot of items. Doesn't matter if there's only 10 items in the array list. I'm just returning a single integer. It's going to take no time at all. Similarly, the isEmpty method, that's just a single Boolean check, checking to see if this number is equal to 0. That's a constant time check. It's one step. Doesn't matter how big this list is, right? All right. On the other hand, adding something to a list is, especially the beginning of the list, is a linear time operation. It takes O of n time. Now, what does that mean? It means that if the list is of size n, then it's going to take around n steps. Maybe it might be 4n, 3n steps, or 2n, but it's of order n. That means that basically that that for every item each item you add adds the same amount of work. So basically if you've got a list of size 10 and it takes 40 units of time to complete, okay? In other words, each item takes 4 units of time to complete. Then in an O of n method, right? That means that adding one more item will take 44 time. So this is an O of n method because say we're adding at index 0. What's going to happen? We do this check. Okay, we got to expand. Okay, so we've got n items in our list. Let's say worst case scenario, our size is equal to our capacity, right? Our list is as big as our size, our list is full. Then we have to reallocate. Well, how long does reallocating take? Well, that means we have to take all n items from the old list and move it to the new list. So that takes n steps. And then we have to shift over n items to make room for the new item we're adding at the beginning. So that takes another n steps. So we're up to 2n steps. So 2n plus these 2 things at the end. Okay, so we call this linear time because once n gets to a ridiculously large number like 100 million, those extra 2 steps at the end of returning and incrementing the size aren't really going to matter in the long scheme of things. It's close enough to 100 million that it doesn't matter. That 100 million is close enough to 100 million and 2 that basically you don't really need to care. Okay, so that's why basically that this method took so long to run. This one over here. Because this is an O of n method over here. So let's go ahead and see let's go ahead and write a much more concrete and easy to see O of n method than the one we have. So let's go ahead and write ourselves a linear search method. And it's called a linear search method because not only does it go in through the list in a linear fashion looking for something, but it's also going to take a linear amount of time. Public static void search. So let's go ahead and search some array list of items. And we're going to see how basically that this will take, some time. So all the same items. Let's go ahead and say public static void, say public static int search. So we're going to return the index of what we find. And this is exactly the same as our, I mean, we've already wrote this method before, but I'm just going to write it again to just, we just wrote this, but write it again for you. It's simply the index of method that I already wrote for you, right? So if we get to the end of this and we can't find it, we're going to return -1, okay? Right, we can't find it in here, we're going to return -1. Otherwise, we're going to return the index of what we found in here. So for, let's go with, so for int I is equal to 0, I is less than list.size. Okay, I is less than list and size, I plus plus. Okay. Oh, and right, I need to put the generic marker over here to say that all these things are the same thing. So if we want to search this list for something in here, right? So if item dot equals list dot get the ith item. Oh, there we go. Return I. So if it's the ith item in the list, we return the index we're at. Otherwise, return -1. So let's just take a look at this. So how long does list.get take to operate, right? Well, let's look at our code. How did we implement it? The get operation, it doesn't take long at all. It just checks to see if the index is out of bounds, right? That's a Boolean check, so that's not going to take a long time at all. And otherwise, we just get something from an array, which, again, does not take long at all. Arrays are really good at being accessed fast like that. So this check's not going to take much time. Let's call it one step, just for simplification purposes. If we find it, return I. However, we need to check every single item in the list, potentially. Okay, potentially, right? If we're checking this item, so say we create a list of random stuff, right? Okay, just a list of random items and we're searching for something in it. Okay, so after we do like a bunch of these searches, some of the times we'll find the item in the beginning, some of the times we're going to find the item in the end, but most of the time that's going to average out to where? Finding the item in the middle, right? We run this a couple hundred times. It's going to average out to finding it in the middle. So on average, we have to search halfway through the list. So we have to search through half of the items. And because we've only got 8 minutes left, I'm going to get into that a bit on Monday, more detail on Monday. But right now, let's just go ahead and see that basically that the bigger I make my list, the longer this is going to take. So ArrayList test. So it's ArrayList of integers. List is equal to new ArrayList integer. So we're going to do this example, and then I'm going to tell you guys the super secret cheat code for figuring out what the how long the O of n for most things are. There's actually a very quick and very easy way to do it, with a caveat that you got to know exactly what make sure you're checking everything, but it's not too bad. So for int I is equal to 0, I is less than, let's say, 1,000, I dot, so I is I plus plus, so 10,000 items, int, so now all we're going to do is simply say list.add I. So I'm going to work on the worst case scenario that basically, so I'm adding the numbers 0 through 9999 here, right, to the list. I'm adding all the numbers up to, but not including 10,000 to this list. So I'm going to cheat a bit, and I'm going to say, let's search this list for -1, okay? Which is not going to find it. So, so let's go ahead and grab our let's see how long this takes test. So, search for list search the list for 13, for a negative 13. Right? And that's not going to take much time at all. Right? It took a millisecond. It took a millisecond to do. Let's go ahead and up that by 10. So it still takes a millisecond. So we're in the realm of this doesn't take too long to do. So 100,000. Let's bump it up to, that's a million. Let's bump it up to 100 million again, right? Did I make it too big? So 100 million takes 2,000. That only took, right, that takes a bit longer because I add it, because it takes a bit longer to add stuff because of the doubling process. And again, it takes, again, about 205 milliseconds. Let's say call it about 200 milliseconds for me to search the entire list for stuff, okay? If I divide this by 10, if I reduce the size by a factor of 10, what happens? The size gets reduced, the amount of time it takes reduced by a factor of 10. What if I reduce it by half instead? Instead of dividing by 10, I divide it by 2. Well, we go from 200 milliseconds to 100 milliseconds, right? There's a linear relationship between the amount of time that that running this program takes and the amount of items in there. So that's pretty nice. I mean, that makes sense though, because you have to check every single one of these n items in there, right? That makes sense to everybody? So how can I tell if I've got a linear relationship going on, or even a quadratic relationship? Well, the answer is actually ridiculously simple, and we'll go into it in more detail. But here's your super secret cheat code. You can count the number of nested for loops. So if you've got one nested for loop, right, and you're going to have to take your function calls into consideration, because if you so I'll get into that in a second. But basically, if you don't have a nested for loop, it's constant time. If you have one nested for loop, and that for loop goes through all n items, then it's going to take O of n time. If you have two nested for loops, like for most of the sorting algorithms that you've learned, and each of those does n operations, then this is going to be n squared time. So this works for most of the cases you'll see, most of the stuff you'll write. I'm not going to say, and it's not going to work for everything, because of course this depends on the for loops basically being for loops that work through everything in the loop, right? So if one for loop was O of n time, right, and two for loops was, and so O of n, remember, is n to the first power. N squared was two loops. What would three nested loops be? Not your question. N cubed. Right. So if you have three nested loops, it's n cubed time. Right? So the number of nested for loops is the amount of time it takes. Now the big caveat to that is, again, that these are basically loops that go through all the items in your collection. So each loop goes through all the items. And the other caveat is that basically you're doing operations inside the for loops. And of course, if one of those operations you do has a for loop inside that operation, so if you call a function and that function has a for loop inside of it, then that might increase it by a degree, right? Right? It makes sense that basically we can't, right? This search call, right? We don't say that this takes we don't say this takes constant time because there isn't a for loop here, right? Because there's a for loop inside of the search function, right? So you got to check your nested functions as well. But this is the quick and dirty rule for this. It's not so mathematical notation. It's actually some of the easiest math that exists. So, and you won't have to deal with it this week. This week it's writing It's basically writing some basic functions. And then next week you're going to deal with doing more of that in a timed lab. So kind of a mini exam. And you'll get and if you're taking math concepts, then you're going to get a double whammy because I'm also going to give you a bit of math homework too. But for once, you're going to get homework that's not programming. For once, in a programming class. Okay. So that's that. I will be happy to take your questions. All right, and then I'll see you next Tuesday. I'm going to go ahead and try to get this uploaded online. So.